wanted to talk about a feature that's a little bit of a makeup for 1.1, where in Cassandra 1.1 we added support for concurrent schema changes, but arguably the most important one of all we didn't address, which is that in 1.1 you can have multiple clients altering your schema across your cluster, except that you can't create column families or tables safely concurrently. So you could alter them, you could add columns, you could add indexes, and so forth. You can do that in parallel in 1.1, but not the actual creation of the table definition itself. So in 1.2, we addressed that finally, and so you can programmatically create and drop tables, for temporary space, or if you're using a table per customer kind of model, that's totally okay. You can do that programmatically now. The next big thing in 1.2 that does tie into the fat node support, but it's useful to everyone, not just people running on large servers, is virtual nodes. So historically, we've had one token per Cassandra server model in our consistent hashing partitioning. So in this example, I have node F colored red here, has one token assigned to it. And virtual nodes, what we're going to do is we're going to split that up across the cluster. And in practice, the default number of virtual nodes is 256. You can increase that if you need to. You can even have different nodes in the cluster have different amounts of virtual nodes, which can help you if you have heterogeneous hardware in your cluster. So you can give newer, more powerful nodes or more powerful machines, you can give them more virtual nodes and they'll take more of the load from your cluster that way. But in this slide, I've just colored in 3 virtual nodes to give you the idea. So the problem that this solves is that it allows operations to be distributed across the cluster in a more fine-grained kind of way. So in particular, there's a couple places where this is particularly important, which are adding machines to the cluster or replacing them if you have a failure. So let's look at the failure case where I have a cluster and then one of my machines dies, and it's not just a bad power supply or something that I can replace and bring the machine back up, but I've actually catastrophically lost all the data that's on that machine and I need to rebuild it. So in the scenario where you have one token per machine in Cassandra 1.1 and earlier, you can rebuild that dead machine from its peers in the cluster that is replicated to. So as is commonly the case, in this example, we have each range of data is replicated to 3 machines in the cluster. So node 5, which is our dead machine, had ranges C, D, and E, and you can see which nodes share those. There's 2 choices for each range that it's replicated to. So what that means is for each of those ranges, we can stream it from its peers in the cluster concurrently, meaning that we can rebuild range C and range D and range E in parallel, but we don't get the benefit of the entire cluster. In other words, in this example, I have 50% of my cluster participating in the rebuild because I have 3 ranges to stream and 6 nodes in the cluster. But as the cluster size grows, if I have 100 nodes in the cluster, and I'm only using 3% of that cluster capacity to do the rebuild. So if I can spread it out across the entire cluster, then my rebuild is going to happen that much faster and we'll get it over with that much better. So when we parallelize this with virtual nodes, as you can see, even in this simple example of only 3 virtual nodes per machine, I'm already able to parallelize that rebuild across the entire cluster because those ranges that I'm assigning to the different replicas are so much smaller and more fine-grained that I can have everyone participate in it. So that's the main idea of v-nodes. It's not about extra performance, really, in terms of what your clients are doing of reading and writing data to your tables in Cassandra, but it's an operational benefit for replacing dead machines or adding new capacity to your cluster, because with virtual nodes, I can grab pieces of data, smaller ranges of data from every node in the cluster as well, and I'm spreading that across the entire cluster as well, and instead of just pulling it from a handful of machines and then optionally rebalancing later. So now we're starting to talk about the features that are specifically for that fat node support that I mentioned. The first of those is improved support for deploying in just a bunch of disk configuration. And the relationship that this has with the fat nodes is that Cassandra is already replicating my data for me, 3 times or however many times I've configured it across the cluster. So having to configure RAID on each machine to replicate that locally as well, that's wasting 50% of my disk space. So if I've got one of these large data workloads where I've got a large amount of relatively cold data per machine, and I want to make the most cost-effective use of my hardware, what I really want to do is I want to let Cassandra manage that as raw disk space and let Cassandra replication take care of repairing anything when disks fail. So that's what this improved JBOD support in 1.2 is about. Is when that disk fails, when I do have disks fail, in prior releases, Cassandra really didn't know how to detect that, and it would keep on trying to write new data to a failed disk, and it would just cause problems in your cluster until you disabled that machine and took it out and fixed it, assuming you didn't have RAID going on to hide that failure from it. So what we did in 1.2 is we added disk failure policies and the ability to recognize disk failures to Cassandra. So when a disk fails in 1.2, you can configure it to either shut down the entire node because you don't want to have that node respond to requests with incomplete information, or you can tell it to go ahead and carry on, but blacklist that failed disk so that we're not continuing to try to write data to it, but we'll only write data to the healthy disk, and that will let us be able to repair the missing disk safely while it's running in the cluster. So the default is for it to go ahead and stop, but if you have if you care more about availability than consistency, then that option is there for you to go ahead and blacklist it and keep running. The next feature that we worked on for the fat node support is to move a bunch of our storage engine internals off of the Java heap. So what that's about is the amount of memory we have available on the servers has by and large kept pace with the amount of disk space that we're trying to address. So it's not really a problem per se that we have these internal structures of the storage engine that require memory proportional to the disk space used. That's not really a problem by itself. The problem is that we've had all those structures on the Java heap, and the Java heap, or more specifically, the Java garbage collector, has not kept pace with the growth of memory, which is to say that Java heaps are basically stuck at about 8 gigabytes to maybe up to 16 is the largest you can make the Java heap before the garbage collector pause times start getting large enough to affect your application in a bad way. So what we want to do is we want to take those structures that we have and move them into native memory off of the heap, where we can clean them up using manual reference counting instead of relying on the Java garbage collector to do it. So
Hi, Jonathan. Sorry to interrupt. Could you speak up a little bit? A couple of people are having a little tough time hearing.
Absolutely. So we've moved these internal structures off heap to allow you to take advantage of the increased amount of memory available on modern servers, is the bottom line. The next feature I'm talking about here isn't related to fat nodes per se. We're moving past that subject here and into more general features related to Cassandra application development and solving the pain points there. So this is the main feature related to application development that isn't CQL specific. So what we're doing is we're taking the concept of Cassandra batches that we've had for forever, and we're making them another level more robust by adding support for atomic batches. So as review, Cassandra batches are sort of the analog to a transaction in Cassandra. The difference is that with a transaction, you have a bunch of steps that happen sequentially, and at any point you have the option to roll back that transaction and say, never mind, I ran into a deadlock, or someone else modified this data out from under me, so I had to abort. But you have that ability to roll back that transaction. Cassandra batches are always, they only go in one direction. You give it the entire batch at once, and Cassandra says, okay, I'm going to make this happen. So there's no concept of rollback. There's just the concept of here's a bunch of updates that I need you to make happen all together. So those updates that you give Cassandra in the batch are still individual rows, changes that you want to make to those. So I've represented those on this slide as 3 different colors, the red, yellow, and blue. And so those different rows in the batch are ultimately going to live on different replicas. So the coordinator, the node that the Cassandra client is talking to, is responsible for piecing those out to the appropriate replica. Now the problem is with these classic batches is if I have a batch like this and then the coordinator itself fails before it completes sending out that batch, then I've basically created this inconsistent scenario in my cluster. What we've said in the past is that the client is now responsible for reconnecting to a different coordinator and retrying that batch to deal with that coordinator failure. But that's the wrong solution. This is really something that the server should be handling instead of pushing it back onto the client. So that's what we're doing with atomic batches, that we basically created sort of a distributed commit log called the batch log that the coordinator will write the batch to before it starts sending it out to provide durability. And so if we have that scenario now in the atomic batch world where the coordinator fails after sending out some of the rows, then the batch log replica will notice, and it will replay that batch on behalf of the failed coordinator. So the client doesn't need to get involved. All the client needs to know is that I gave you the batch. Now it's your job as the server to take care of it, and I don't have to worry about it anymore. So this is actually the default now in CQL batches. So if you say begin batch in CQL, then you're going to get an atomic batch. If you want a non-atomic batch, if you want the old behavior, you actually have to say begin unlocked batch, and that will give you the old behavior, which is there's about a 30% performance overhead to the atomic batch log. So if you're 100% certain that it's okay if you get partial batch completion, or for whatever reason you're okay with that, then yeah, you do have the option to fall back to the old behavior and get that slight performance edge. But in the general case, we think that it's more important to do the writing by default, the spacing by default. So we made atomic behavior the default in CQL. Now, we didn't really have that option for the thrift API. So what we did was we added a separate thrift method. So you have a batch mutate method for the old behavior, and we added a new atomic batch mutate for the new behavior. So those of you using Thrift clients or Thrift-based clients, will want to be aware of that and how those different clients decide to expose that. So that brings us to the CQL updates that we've done in 1.2. And this is where we've really gotten a handle, I think, on the common pain points that people have with doing data modeling with Cassandra. We've basically been exposing the Cassandra storage engine more or less directly to people and saying, here, make sense of this and write your app so that it makes sense for the Cassandra storage engine. And we've been reasonably successful with that approach, but I think long term that we don't want to do that. We want to be able to give people a more familiar model and take care of mapping that to the storage engine kind of under the covers and let people not have to worry quite so much about the implementation details of comparators and composite columns and so forth. So to do this, we've done a couple things. We've fleshed out the support we had for compound primary keys and mapping user-facing tables to storage engine column families under the hood with that. And then we've also added new features like collections to allow you to more easily handle common scenarios of denormalization in your application code. So this page here, this slide here, this is actually legal. It's legal both SQL and CQL in both Cassandra 1.1 and 1.2. So this is like the easy case where I have a table of it's just a simple primary key. I just have a handful of columns that I don't need particularly to partition in any particular order. So this is a really simple example that we've been able to do for a while. And what I'm going to do now is talk about how 1.2, we're not fundamentally changing what Cassandra does. We're not trying to make it more of an SQL. We're not going into joins or anything like that. What we are making it able to expose Cassandra's strengths in a way that makes more sense. So to talk about that, I want to give an example of a song and playlist manager and show how we go from the thrift and command line based schema to CQL 3-based schema in Cassandra 1.2. So the first column family or table that we're going to talk about is just the songs data itself. So this is what the definition looks like if you're defining it with the thrift-based command line. So you say create column family songs. I give it a key validation class. I've colored the keys light green on this slide to show that that's distinct from the column data. And then I give it a comparator. And then for each column, I give it a column metadata entry with a name and a validation class. So, okay, so this is still fairly straightforward. It's kind of verbose and a little bit clunky to remember the syntax, but it's fairly straightforward. And mapping that to CQL is also straightforward. So this becomes create table songs. I have a UUID primary key, and then I have some columns defined. And I've left data off because that's just a binary blob. I don't want to put 3 megabytes of data on the slide, but the other 3 columns are represented here. So if you look between those two, the representation of the data on disk, where I have cell name and then cell value, and I've got those sparse, the cells are defined sparsely. So with each cell, I have to repeat. I have title and for each title cell, and then I specify artist for each artist cell, and I have to repeat that in my storage engine cells. So when we move to the CQL representation, now this looks a lot more familiar because we have my columns. I define my columns up front, and then I just need to list the column value for each of those. And and you can see how the table definition itself is that much more compact and straightforward. Now here's where things start to get more interesting. When I start talking about how in CQL you define your columns up front, then people who are familiar with earlier versions of Cassandra, start to get worried and saying, well, are you going to take my dynamic columns away from me? No, we're not doing that. We're just helping you represent them in a more straightforward fashion. So here's an example of what I mean by that. One of the things we want to do in our little playlist manager is allow users to add tags to their songs. So in here's the thrift definition again for that. We're going to have a song tag column family. We're going to give it a key validation class and a comparator. So this is an example of what we used to call dynamic column family. I don't have any column metadata specified because each of my cells here is going to have a name that's determined at runtime by whatever the application decides to insert. So my cell name and my column name at a user level are not going to correspond one-to-one anymore. So here's an example of some data there, where for the first song I've added tags blues and 1973, and for the next one I've added a tag covers and a tag for 2003. So I've got 4 tags across 2 songs represented here. So this is the part where your brain explodes a little bit. And so if you can get this, then you're in really good shape. So how we map this to a table in CQL3 looks something like this, where we're going to go ahead and say create table song tags, and we're going to give it the ID for the key, and the tag name is going to be our new column name. And then we're going to give it this compound primary key definition that we haven't seen before, where I'm going to say both the ID and the tag name are part of my primary key. And so how that translates into the storage engine world is I'm going to take that primary key definition and take the first element, so the ID, that becomes the storage engine row key, or what we call it in the CQL world, the partition key. So you can see that the A36 UUID, we have a single storage engine row that becomes multiple rows that are exposed in the CQL result set. In fact, we have 1 row per storage engine cell. And the storage engine cell name becomes the tag name value in the CQL result set representation. And so note that I've put an orange box around the parts that correspond here, the parts that go together. So basically, what the CQL partition that we're going to guarantee all goes to the same server, so you can fetch it efficiently. That's colored orange. So we've taken that 1 orange storage engine row and we've split it up into those 2 rows in the CQL result set, and I've still boxed them in orange to show that that's where those are coming from. It's coming from the same storage partition. Now, one thing that does come up is, can I then have a partition key that is itself composed of multiple columns? And the answer is yes, you can. You use parentheses to denote that this first group of columns is actually a composite partition key. but we're not actually going to show that in our example today because that's a little bit more of a niche kind of feature. But the take-home message from that is that in moving to this representation in CQL3, we've been very careful to make sure that we're not actually losing any functionality. So if at any point in this you get the impression that, hey, it looks like I can't do something that I used to be able to do from Thrift, then it's probably my fault for explaining it poorly, because that's been our goal the whole way through, to make sure we're not losing any functionality. One more example that gets a little more complicated. Before that, before the one more example, one of the things we added in 1.2 is collection types. So you can define columns to be lists or sets or maps, which gives you an easier way to denormalize than pulling things out into a separate column family. So for the song tags example, in 1.2, I could just say alter table song and then add a tagged column that was a set of the tags. And so that would look like this, where instead of pulling those out to a separate table, I now have a tagged column and the data in it is a set. And that's how sets are represented in CQL, by the way, is as curly braces around comma delimited data. And lists are bracket delimited, and maps are curly brace and colon delimited. Basically the way you'd expect from JSON if JSON actually had a set type. So we kind of made up our own syntax for that, since that's not part of the JSON standard. But under the hood, this is more efficient than having an actual JSON blob would have been in earlier releases, because what this lets me do is I can say update song set tags equals tags plus, and then some more tags, and then only those new tags will get appended to that column at the storage engine layer. I'm not having to rewrite any existing data, which is what you had to do if you were taking the JSON blob approach in prior releases. So the last example I wanted to talk about here was the playlists themselves. So the way we do that in the Thrift world is we're going to say that each song in a playlist is going to be this composite column where the cell name is composed of the different pieces of data that we want to track for that song. So that's what we've got here, where the comparator is a composite type of 3 UTF-8 components. And so one of those components is the title, one is the artist, and one is the album. So that's how those map to that storage engine row. So the way we map this to the CQL world is similar to how we did it with the song tags, where we're going to have a compound primary key. The difference is that now that we're dealing with these composite columns, we're actually going to separate out each of those components into its own column. So the artist becomes its own column, the album and the title both become their own columns that we're pulling out of these composite entries in the storage engine. So do we have any questions so far, Christian, from the audience about this? This is a good time to actually take a mid-presentation break about the CQL transformations that we've done. All right, so moving along, if you do have questions about it, then we can still take them at the end with everything else. So there's one more piece about the CQL mapping of tables to storage engine column family that's worth discussing. And that is that how CQL exposes the comparator. So the comparator is what we use with these dynamic column families to make sure we get the results back in the order that the application wants them in.
So, Jonathan, sorry, I was trying to get myself off of mute. So, related to CQL, Jeff Schmidt is asking, what about client-side non-thrift access?
So, CQL is a query language that's kind of transport agnostic. So you can perform CQL queries over thrift. There's an execute CQL3 query method in thrift that most of the existing clients use to access CQL. We've also added for 1.2 a native CQL protocol, but part of the upgrade path that we want to provide is we don't want you to have to rewrite your entire application on top of a new native protocol client to access any of this. So there's definitely the potential for a gentle upgrade path by continuing to use the Thrift API in your client that your application is built on, and then adding new features in CQL if that makes sense. And clients like Hector on the Java side, Picasa on the Python side are taking that approach of exposing methods to perform CQL queries from basically a Thrift base. Now, it's also worth pointing out that the ability to access data that was created in one way or the other is bidirectional. So I've been talking about here how CQL is basically able to access data that was created from Thrift. So in any of these examples, for instance this one, I can actually pull data out of this column family from a CQL query without having to go through and do this create table. So if I already have this column family defined, I can go in CQL and say select star from playlist, and what Cassandra will do is it will assign column names to those different composite components. So you'll get it back with column 1, column 2, and column 3 instead of artist, title, and album. And then you can go ahead in and say alter table playlist, rename column 1 to title, and rename column 2 to artist. And you can give CQL that extra metadata without having to do any rewriting of your data on disk. And you can access things the other way as well. If I create this playlist table, I can still access that data from Thrift if I understand how that's mapped to the storage engine under the hood. And playing around with the command line interface can help with that. The CLI, you can say list playlists if you created this table from CQL, and then see that data and how that's been mapped into the storage engine structures. Are we good to continue, Christian?
Yes, thank you, Jonathan.
All right, so the last piece of this puzzle is how does CQL handle exposing the comparator and ordering rows to the CQL world, ordering rows within that partition. So in the playlist example, we didn't particularly care about what order our songs are stored in. I'm not sure that maybe we could store them in chronological order or something, but I think an example that makes a little more sense intuitively is to talk about something like Twitter or something like Facebook, where I'm following my friends and I want to see their update in some kind of chronological order. So here's an example of a way I could store a Twitter timeline, meaning the tweets that my friends have made in Cassandra. So I'll have create table timeline, I'll have user ID, that's me, that's the person whose friends' tweets we're tracking here. And then we'll have tweet ID and tweet author and tweet body for each tweet. So the tweet author is the person who made the tweet, and then user ID is the person who's following him here. So what I want to do is, I want to get a list of all the tweets of people that DriftX is following, and I want to get those in chronological order. So what I do is, in my compound primary key definition, the user ID, that's my partition key, that's the first entry, but then any other components, any subsequent components of the primary key, those are going to get turned into the comparator. So by having this user ID, tweet ID primary key definition, I'm saying that within the user ID partition, tweets should be sorted by tweet ID. And since I've defined tweet ID to be a time-based UUID, a version 1 UUID, then I'm going to get those in chronological order. So when I say select start from timeline where user ID is DriftX, I get that back in chronological order. Don't have to do any work, I don't have to do any sorting at runtime to get that. In fact, in CQL, I could optionally say order by tweet ID, or I could say order by tweet ID descending. Both of those are fair, and by default it will perform an ascending order by on the remaining components of the primary key. All right, so switching gears just a little bit, but still in the realm of what we've done with CQL, we're moving towards exposing more of the information Cassandra has about itself through CQL. So there's a couple categories of information that we have. The first one is about the schema and the table definitions that we have, and then the other is more about, what other nodes are in the cluster and what do I know about them. So for the so all of these, by the way, all of these are going to be in the system key space. So that's where I'm doing these queries from in this example. So for the schema, we have 3 tables in the schema key space that deal with schema information. So the first is schema underscore key spaces, and that looks like this. A fairly simple a number of pieces of data about each key space that we have defined. We also have schema underscore column families and schema underscore columns. I won't show example data for those because there's a lot more columns in each of them. But that's where that data about the tables you've defined is stored. Now, one other thing that's worth pointing out here about the strategy options and other places where we have kind of a set of options in the schema, for instance, with compression options or compaction options, both of which are per column families, we've changed those to be maps now that we have this native map data type to do that with in Cassandra. So the syntax has changed a little bit. So the way you would define that now is with the map syntax of curly braces and colons, the way you see it defined, the way you see it coming back in this query here, rather than with the old kind of ad hoc colon delimited option syntax from 1.1 and earlier. Then the information that we have about the cluster itself, we have 2 tables for that. We have the local table, which is about the node or the machine itself that we're talking to. And then with that a slightly thinner table is the peers table, which is everyone in the cluster, what do I know about them? So you can see in the peers table, we know what their network address is, what schema version they know about, what data center and rack they're in, and their token, which you'll note because of the virtual nodes, token is a set rather than a single entry. But compared to what we know about ourselves, we know a little bit more. We track some metadata about truncation time. That's actually a map of table IDs to the truncation times is what that is.
So Jonathan, I have a question that's sort of related to this from Aditya. Where is the CQL metadata kept, i.e. title, album, artist, and case composite columns?
Yes. So it's effectively, the short answer is yes. It would be in the schema underscore columns, and you can play with that and kind of see how that looks. But yes, that's where it is. So the other thing I wanted to point out here is that this gives you everything you need to know about how Cassandra routes your data to the different replicas in the cluster. So in the local table, I store what partitioner I have. In the key spaces table, I store what replication strategy I'm using. And then in the peers table, I have the data center and rack for each machine in the cluster. So given those pieces of information, a client can actually determine for a row that it wants to query where that row lives in the cluster and use a connection pool to connect to a node directly that has that data locally rather than going over an extra hop through a coordinator that doesn't have the data locally. So Hector of existing clients, SDNic, clients like that like to do this already. And so again, our goal with CQL is to give you all the functionality that you've had exposed in a more ad hoc basis over Thrift, such as the Thrift describe ring method call, and still give you the ability to do that kind of advanced connection pooling with CQL-based clients and the native protocols. Lastly, I wanted to cover more of a troubleshooting feature that we've added for 1.2 that's well integrated into CQL, but it's also available over Thrift, which is request tracing. And so what this does is, in CQL shell, you can say tracing on, and then Cassandra will collect tracing data for each query that you do from that session until you turn it off or disconnect. And here's what that tracing data looks like. And I've gone ahead and colored it to make it clear that which machine each line is coming from. So the trace starts off in blue. That's the coordinator I'm talking to from CQL shell. It's the 127.0.0.1. And then it's going to, the coordinator sends that request to a replica node in the cluster that's .2, and that's colored in red. And then the replica machine sends the reply back to the coordinator, back in blue, which will then give it back to CQL shell. So that's kind of the life cycle of the request, of a very simple request here. Now, if I wanted to do this from Thrift, what I need to do is I need to call the trace next query method, and then Cassandra will collect the tracing data into the system underscore traces key space, and then you can pull it back from that programmatically if you're not doing this from CQL shell. But I wanted to give an example of how this can be useful. One kind of common anti-pattern that people come up with when they're first exposed to Cassandra is, hey, I've got data partitioning and ordering within that partition, so that gives me a really, really simple way to model a persistent queue. And so people will model a queue like something like this. It's transformed into a CQL table. I'll say create table queues. I'll have the queue name be my ID, and then I'll have, for each entry in the queue, I'll have a created at column, and then an opaque value, so something like this. And then since I'm telling it to use this compound primary key with created at being the sorting part of the primary key. And that tells me that for each queue I have, each queue is going to map exactly to one Cassandra data partition, and the entries in the queue will be ordered by created at. So far so good. The problem is that since Cassandra is this distributed system, deletes are not instant. We need to keep these things called tombstones around so that if any of the other machines in the cluster miss the delete, we can replay that delete to them rather than having that machine that missed the delete replay the original data back to us and have it reappear, which we don't want. So what I've represented that on this slide as striking out the deleted entries. So they're still there in the sense that we have a tombstone saying that this entry doesn't exist anymore. But if I do a select query from it, then they won't be included in the results because they've been deleted. So if I go ahead and insert 100,000 entries into this queue and then delete all of them, and then I go ahead and run my select next entry from the head of the queue, which is this query at the top here, then what you will see is as the number of entries in your queue that you inserted and deleted, as that number increases, your query slows down. And request tracing shows you what the problem is. So this line that I've highlighted in green here, that to execute this select limit 1 query, I still had to read 100,000 tombstones to get that before I found a queue entry that hadn't been deleted. And so that took the elapsed column. The elapsed column is in microseconds. So that took 35,000 microseconds or 35 milliseconds to do that. And so this is a common mistake that we see at DataStax and people doing data modeling. Is things like this that we're hoping that request tracing in 1.2 is going to help people figure out what's going on and see where the problem is before it gets to be a really critical problem in production. So at this point, I will switch tabs here that we have training available, and you can find out more about that at the URL here, and we'll turn it back over to Christian for more questions.
Yes, thank you very much. So we have about 10 minutes, and we've got some questions coming in. If you would like to ask Jonathan a question, please go to the Q&A tab in WebEx and type your question there. I'll read them out to Jonathan, and we'll try to get through as many as we can in 10 minutes. So let's get cracking. The first one from Jerry, this one is regarding vNode. With vNode support, can we reboot n is greater than RF number of nodes at the same time safely? Can we control the distribution factor?
That's a good question. And vNode is basically separate from your replication factor. So you're still going to have the same number of replicas across the cluster. The difference is that instead of having the same 3 or so nodes replicating all of your data that you're responsible, all of a given range of data, we're splitting that range up into much smaller pieces and scattering those across the cluster. So instead of sharing data with 3 nodes, you're sharing data with the entire cluster, but each other member has a much smaller piece that it shares with you. But the number of replicas you have total is the same, and so the guidance on you can't lose more than 1 machine and still be able to do quorum reads with 3 replicas is unchanged.
Great. I can take the next question. I love it when I can answer a question. This is from Kevin. Is this webinar available for viewing later? Yes, it is. All of our webinars are available for viewing both from the datastax.com website and also from the new community website, planetcassandra.org. We try to get the archives up and posted within 24 hours, and we will email you when the archive is available. Okay, next question for you, Jonathan, from Victor. What about moving mem tables to off-heap to minimize young generation collection pauses? And then in parentheses, he has par new GC, for instance.
So we've actually explored that. We've actually explored moving mem tables off heap as well. The problem is that the reference counting we need to do for that gets really, really hairy, because what we want to be able to do is we want to be able to free that memory up as soon as it's flushed. But if we have a client request that is using that memory because it was accessing that mem table while the flush was happening, we can't, even if we finish the flush, we can't free that memory up until any requests that were accessing that mem table are also finished. So there's just because of the way the code's organized and how that works out, excuse me, that's a pretty hairy thing to tackle. And so what we've done instead is when you add data to a column family and it goes into the mem table, we actually copy that into a large byte buffer that are, we allocate 1 megabyte size byte buffers and then copy your data into those. So we're basically doing arena allocation within the JVM. And what happens is those arenas that we've created, those megabyte-sized buffers, those get tenured fairly quickly. So they don't interfere with your par new anymore after a few minutes of being up and active. So ideally, I would like to cut the heap footprint even further by moving those off heap. But I think what we're doing is a good compromise between complexity of implementation.
Okay,
and,
great. Let's see how many more we can get through. This one is from Tamar. Any hints on how to upgrade a 1.0 setup to 1.1 and then to 1.2?
So let's see. Basically, the only hint you need to know is that you want to be on the most recent minor release of your series before upgrading. And if you read the news.txt file, it'll have details on when exactly this is necessary. But as a rule of thumb, it's best that if you're on 1.0, then upgrade to 1.0.10 or whatever the most recent 1.0 release is, and then you can jump straight to 1.2 from there. You don't, so far, let me put it this way, so far, we've never made you stop, or we've never made you do intermediate upgrades. We're still fully backwards compatible at the disk layer all the way back to 0.6, I think. But you do want to be on that most recent minor release, because sometimes there's network protocol issues where it's not compatible with doing a live rolling upgrade of part of your cluster at a time unless you're on that most recent minor release.
Okay, and I don't know if you have the answer to this one yet, but it'd be interesting. This is actually a DataStax Enterprise question. When can we expect 1.2 in DataStax Enterprise?
So I can give you a historical perspective on that, where with DataStax Enterprise 2, we first released that on 1.0, and then we did a minor release of DSV2, I think it was 2.1, where we released it based on Cassandra 1.1 release. So we're going to see the same thing, I expect, with DataStax Enterprise 3, that first it will be released on Cassandra 1.1, and then we'll do a minor upgrade or a minor release that incorporates Cassandra 1.2. As to how long that will take, All I can say is our goal is to be faster than it was with the 1.0 to 1.1 migration.
Okay, thank you. From Richard Goldman, any comments please on the abilities or limits of Cassandra 1.2 JDBC driver to locate available clusters, and to what degree is load balancing implicit? Any examples or general comments on driver hint config toward this would be appreciated.
So let me grab this link for you. I'll paste it into the WebEx area. If you want to play around with CQL from Java, let's see. I'll paste it into chat, I guess.
Go into the Q&A panel. Oh yeah, there it came. The GitHub link. Yeah.
We released a Java driver using the native CQL protocol, and it's a JDBC inspired kind of API, but we've cut out the parts of JDBC that don't really make sense in the CQL world, so basically it's cleaner, it's simpler, and it does all the connection pooling and smart request directions that you'd want. The JDBC driver itself, if you really want to use that, I don't think it does anything particularly special around connection pooling. It may even push the connection pooling off and say you're responsible for doing it yourself or with some other library. You really need to ask the JDBC project about that. I'm not super familiar with it at this point.
Okay, we're at the top of the hour. Can we squeeze in one more? How is the data distributed over JBODs?
So basically, we try to keep the disk space utilization even across the disks. So yeah, it's basically a leveling algorithm where whoever is emptiest will try to allocate data on him. But it's also aware of workload where if I'm already writing one SS table to this disk, I'll write the next one somewhere else, so I'm not overload. If I add a new disk that's empty, for instance, I don't want to just brutally hammer on that and make that the bottleneck of everything. So it will even out the disk utilization over time, but it doesn't.
Okay, Jonathan, thank you so much for taking the time today. Just a reminder, this webinar will be posted tomorrow as an archive, and join us for our next webinar in the series, which is, I believe, in 2 weeks' time, and is CEP CEP streaming with Storm and Cassandra. So we'll look forward to having you back then. Or it's next Thursday, January 17th. Thank you, Paige, like magic. So have a great day, everyone. Thank you.
Thanks, guys.